Bismillahirrahmanirrahim. Assalamu alaikum. Hope you all are fine. Today we will present on force measurements. I am Salman Yunus and my group member is Mr. Samiullah. Here we have a list of the force transducer. Some of the force transducer will be covered by me and the rest of the force transducer will be presented by the Mr. Samiullah. Now we discuss the mass sensors. There are actually no such mass sensors. This is quite surprising for all of us. Let me take an example for you. So, as a generic example, you go to the market and ask the shopkeeper to have the 1 kg of the fruits. He used a weighing instrument to weigh it, to weigh the apples, and said me that he has weighed the apples about the 1 kg. You think at that spot you ask him to weight it, and he is telling you in terms of its mass that is a 1 kg. And how is it possible? Actually, it is possible. You can indirectly relate the mass in terms of its weight by using the well-known formula W equals to mg. In daily life, we can relate the mass in terms of its weight by saying at 1 kg of the fruit or something else. It is also referred as its weight. So actually, whenever you come across the phenomena to measure its weight, then we use the formula W equals to mg, put the gravitation value of the earth and multiply with mass given and evaluate the force in terms of its Newton. So whenever the deformation has to be measured of some objects, then you need to convert the mass into its force factor, into its weight factor by using the relationship, so that the sensor can easily observe or sense that the force and produces the output corresponding to it. So application of the force will produce some deformation in especially designed elements like the strain gauge, piezoelectric materials, piezoresistant materials, and more than that of it. And this deformation may be measured using the various type of the sensors. And sensors that we actually applied, that's strain gauge, transducers, and piezoelectric sensors, and LVDT for the displacement measurements or force measurements, and more than that of it. In next slide, we'll discuss about the strain gauge factors phenomena. Now let's discuss the force measurement techniques or methods. It is classified in two main categories. One is a direct method, and other one is an indirect method. A direct method involves a direct comparison between two masses or weights, in which the unknown force weight is measured on one pan. Like in a daily example, we can see a known gravitational force on the standard mass is taken place on other pan or the weighing instrument, and equivalent position is achieved to have the known weight of the unknown mass. Like beam balance, pendulum balance is an example of it. Indirect method, it was an indirect comparison of the force that has to be measured through some sensors that senses the weight, like load cells, displacement transducers, and more to discuss on than that of it. Deformation due to the applied force applied on lasting member is measured. Actually, almost all the transducers that I discuss are usually made of the elastic element. Elastic element are those elements that possess the elasticity in its behavior, linear behavior of following the Hooke's law during its measurements during the whenever force applied. As a result, it produces the strain or the elongation or compression in its output during its elastic limit. So actually all the deformation are basically measured in the elastic limit of the instrument. Now discuss the indirect force measurement methods. Now we have the famous cells known as the load cells, also called elastic element. They use a physical and main principle that the force applied on elastic element produces a measurable deflection and obeys the Hooke's law. In that, whenever a force is applied on any type of material like the iron, steel, or other type of the piezoelectric material, piezoresistive material, it produces a deflection. And deflection is such that whenever the force is removed, it regains its shape. So in a sense, it obeys the Hooke's law. Whenever the force limit is boundary or this limit, then it never can obeys the Hooke's law. Elastic elements are commonly used, especially shape and design in structure. Load cells exist in both compression and tension forms, and the advantages are they are being relatively low cost, have the wide measurement range and also have tolerance of the corrosive environments, remote measurement capability, tolerance of shock loading, easy of installation, and the main disadvantage of the load cell is that may cause a permanent deformation may occur, adding bias in reading. Means that whenever you have go through the limit of the Hooke's law or a specific point that is known as a P point, at beyond that limit you may see there is a permanent deformation in the structure of the elastic element and does not further obey the Hooke's law. At that point, there is a bias added to the structure. Whenever a force is applied to it, there also exists an initial reading to the of the deformed structure. So in sense, the measurement range also reduces to some extent because of the initial bias, initial zero error is reduced in the load cell. There are different forms and shapes of the load cells. There are two main categories of the load cells: block type and ring type, or frame type, also covered in approved ring type load cells. In block type load cells like this one and this one, they are used to give the measurable deflection upon applying the large amount of the force on them. That is, they are not force sensitive. They work only when large amount of force applied upon them. In the same sense, when such amount of the force applied on the proof ring or proving frame or other structure like that, they will deform permanently because they will never obey the Hooke's law. So we can say that proving frame or proof ring are sensitive to the forces that gives the measurable amount of deflection. They operate for a lower amount of the forces applied, and they work for the large amount of the forces applied. Now the question comes in mind, how can we measure such type of deflection? Deflection can be measured very well known gauge known as the strain gauge. Before discussing the working and type of the strain gauge, let us first discuss the important concepts relating to it that want to recall its terminologies that are links with the strain gauge. Let's take a quick recall of the strain gauge terminologies: stress strain, Hooke's law, Y resistance, Poisson relation. As I already know that most of you are well familiar of it at intermediate or metric level. So stress is force per unit area on the particular material. As a result, there is some deformation produced, which is measured by the strain, which is a ratio of the change in length over the original length. Hooke's law for elastic material stress is linearly proportional to the strain, as represented by the formula stress equivalent to the elastic modulus into the strain, Models of elasticity has three format: Young modulus, buck modulus, shear modulus, depending on type of the force applied, maybe the axial force, shear force, or the normal force. And other one is the wire resistance. And well known equation, we know that R equals to the rho resistance of the wire is equal to the resistivity of the wire and the length of the wire upon the cross section area of the cross section of the wire. And the Poisson ratio, we also know that Poisson ratio is a deformation, or it can be expansion or contraction of the material upon the in a particular direction of the specific loading, that is the lateral strain over the axial strain. If we take example of the cylinder, when it is extended along the length, so length increases, so we can its length is axial strain, as we taken the axial along the length, and whenever its diameter decreases because of increase in length, we call it lateral strain, and minus sign comes to the fact that there is a decrease in the diameter. So we have this type of formula. There is another factor known as the gauge factor, the strain gauge. It is defined as the ratio of the fractional change in electrical resistance to the fractional change in length. It actually defined as sensitivity of the strain gauge. That how much is a change in the resistance of the strain gauge whenever there is a change in the length of the strain gauge wire. So a generic formula used in different scenarios. It is a basic formula that will be used in different types of the beams, cylinders, or different geometries having different gauge factors. Actually, gauge factor is meant to define that sensitivity of the strain gauge, how sensitive is to measure the resistance, is to give the change in resistance whenever there is change in the length of the strain gauge. The values of gauge factor may vary depending upon the change in the strain. Typically, it has the 1.4 to 2 gauge factor metallic strain. For semiconductor piezoresistor, it has almost about 200 gauge factor. It is a more sensitive, and the metallic strain are less sensitive. It has less gauge factor number. Let's evaluate the gauge factor of the metallic cylinder under tensile stress in the next slide. Now let's drive the gauge factor for cylinder under tensile stress. As I discussed in the earlier slides, that the gauge factor has a generic form that is utilized in most of the geometries to take up the form of different kind. Here we have discussion of it. Here we have the cylinder that is applied by two opposing forces having the initial length L, and then we have this kind of differential length and the change in the diameter. As we already know that this kind of the expression of wire resistance in previous slides, we take differential of this and with respect to the tensile stress, and we end up with this form. And here we had a change in resistivity, as we already know that resistivity depends on the material, but in some of the cases, in some of the material, it changes with a change in length or change in the resistance. We simply divide the above expression with R to get this form, and replace above expression with this wire resistance formula. We also applied the area formula of the cylinder, and after that we have also used the Poisson ratio, which is the decrease in the diameter with respect to an increase in the length of the cylinder. After some formulation, we end up this formula before the gauge factor to be applied. Here we have the differential change in length dependent upon the change in the differential change in the resistance depending upon change in length, and the Poisson ratio and the change in the resistivity. After gauge factor, we end up this formula that depends only on the Poisson ratio, resistivity, and the strain factor that is utilized in some of the calculation of the cylinder and the tensile stress. Here are some of the gauging techniques that must be keep in mind when you're using the gauges during the installation. That is first one, the installation, that the gauge size matters a lot, and it should be selected such that the bonding between the substrate and the gauge must be appropriate, and the size must be appropriate depending upon the loading surface. And second one is the hysteresis. as there is a continuous use of the gauge uh, during the operation, during the work, so its stresses can be avoided uh, by by simply increase the load factor beyond its range, or beyond, that is increasing its strain beyond its certain limits, and also can also be avoided by the preventing the fault bonding between the gauge and the loading surface. And third one is the fatigue life. Fatigue life often arises due to the stress reversal that occurring at the leads of the gauge and cause decay in the back of the gauge. For the dynamic purposes, we often use file gauges for testing. And before we have the humidity effect, moisture can badly affect the bonding between the gauge and the loading surface, that can be avoided by simply heating the surface. The creep in creep we observed that in some of the instances when we change the load, continue to increase the load on the string or gauging parameter gauges, there is a increase in the strain, but after some time the strain becomes constant. It's called positive creep. And in negative creep we have the reverse effect, because there is a decrease in the output, the increase the load. Creep is more significant in the smaller gauges, and so we must use the larger type of the gauge, so this effect should be minimized. Now a question comes in mind: what is a strain gauge? A strain gauge is a device which is used to measure the fractional change in length over the original length, which is mounted on the structural member which is under stress. They are mostly used to measure the force or strains on the free body of the surface. It used to measure the strain in three categories: the shear force type, compression force, and tensile force. Usually there are different types of strain gauge. We will discuss each of them. The strain gauges are classified into broadly three groups on the basis for the magnification of change in length. We have mechanical strain gauges, optical and electrical strain gauge. In mechanical strain gauge we have type of the extensometer. Here we have type of the arrangement over here. Here we have the specimen placed in the end connected with the spring, and we have a dial indicator connected with the lever. When there is a axial force applied at the both ends of the specimen, there is a relative change in the knife pointers. As a result, this relative displacement is amplified through the lever arrangement, and is indicated by dial indicator, which indicates the change in the length or the change in the strain. Two forms of the optical strain gauge: Martens and Tuckerman optical strain gauge. In our Martens optical strain gauge, we have the specimen placed over here and two knife edges. Other one is the mirror A type, and when the levers are connected with it, when there is some deformation in the specimen, it is reflected in terms of relative displacement of knife edges, and the light entering into the mirror can be presented as a deflection on a scale B. In other type we have a Tuckerman optical gauge, which is more modified version of the Martens gauge. In that it has autocollimator, has a lamp which generates the photons, and after reflection from the mirror it creates some measurements on the scale that can be recorded. Electrical resistance strain gauge is a passive transducer that converts the displacement produced due to the force into corresponding change in resistance. Means that whenever there is a change in the strain or change in length, this change in length is reflected in a change of the resistance. It is specific inherent characteristic of the strain gauge. It's most commonly used device in most of the applications, like our manufacturing industry, robotics industry, as also used as tactile sensors. The other feature is that it also has designed to measure the strain along the specified axis, so this having different forms and a linear, as shown in the figure, a linear one, a T roster strain gauge, in which the strain gauges are placed in 90 degrees shift, and a T roster strain gauge and V shape strain gauge that are used to measure the strain in different orientations. and also have the different types, that is semiconductor strain gauge and the foil type strain gauges. And semiconductor strain gauge are more precise when they foil type, they have the high gauge factor as compared to foil type strain gauge. And also had a good sensitivity of the semiconductor devices strain gauges as compared to foil type. Circuits for electrical resistance strain gauges, there are two major circuits, blast circuits and Wheatstone bridge circuits. It has a three more bridge circuits named as a quarter bridge, half bridge and full bridge. Each of it has advantages over the other. Let's moving towards the next slide. On next explanation, focus upon this graph. Here we have the applied strain, when the actually 4 strains applied, and it's measured strain by some instruments, by some sensor. Actually the response should be linear one, but we got the non-linear curve as shown by dotted line. There is a deviation from linearity. This linearity may be due to the main factor called temperature factor, that may be compensated by certain strain gauge techniques by using the dummy gauge with the active strain gauges discussed in the later slides. As you can see, there is also a hysteresis involved during the load condition and unloading condition, and as a result there is a zero shift in zero reading at the initial reading. So in a sense, whenever there is a strain measurement, there is also always an non-linear relationship between the measured strain and applied strain due to the factors of temperature gradient change and also other environmental factors, the main due to the temperature change. However, the bridge circuit as shown in figure is further amplified by instrumentation circuits by signal conditioning. Is amplifier, which is again otherwise detector detects the signal or indicator. It may be indicator used by some sensor or recorded that signal. So in the instrumentation part or the signal conditioning part, here is the main part that converts into voltage form, that is be led by the amplifier for amplification. We have the blast circuit. The strain gauge blast circuit consists of a simple circuitry involves the input voltage and a blast resistance series with the strain gauge active resistance, and we want to measure the output voltage E0. We apply the simple Ohm's law and we get this relation of the output voltage, and simply as we know that there is a change in resistance that results in a change in the output voltage, we simply take the derivative of the above expression and by applying the quotient rule, and simply we get this ended up this relation. And we now know that sensitivity is a change in output voltage, a change in resistance, so we get this relation by putting the values of the differential V and differential R. And now to determine the maximum value of the sensitivity for this, we have to determine the blast resistance. So this we simply take the differential test, and after the differential test we get a condition R equals to RB. Is that condition we get the maximum sensitivity of the blast circuit. And after some formulation in the main equation, we get this factor when the relative change in the voltage respect to the input voltage is equivalent to 1/4 factor of the resistance, meaning that it's a lower sensitivity as compared to the other circuits. And also it has the main disadvantage that it is always in the state of the unbalanced state, that is that gives the voltage the value whenever there is no force applied. It also having a biasing in the circuit. So we move to the Wheatstone bridge circuits. The first to discuss the full Wheatstone bridge circuit. They have the 4 resistances. Strain gauge is active strain gauge resistance. These resistances are placed in such that the R3 and R2 in the compression mode, while the R1 R3 in the elongation mode, when the 2 in the stress and 2 in the other way in the unstressed mode. It depends upon the states in which they are the placed. in the on the cantilever beam or some other beam like that. All we know that Wheatstone bridge from the intermediate level that R1 equals to R1 R3 equals to R2 by 4 is obtained by the voltage division rule across the A, B and D point. And we know that when there is a force applied on all the four active resistance, is a change in resistance which is reflecting the change in the voltages. So we now to determine the output voltage equivalent to VBA minus VD, simply put the values of the VBA and VDE in this relation by simply voltage division rule, and we simply replace R1, R3, R2 and R4 by the variants, as I say R1 likewise R1 plus delta R1, R2 delta R3 and so on, and by some formulation we get this relation where we can replace this factor by P as it is a constant factor. Finally obtained relation. The full bridge circuit is more sensitive as compared to the other bridge circuit, but it's costly. The all active strain gauges are required, and also it has a benefit of temperature compensation. When there is a change in temperature, all the resistances of the strain gauge also change correspondingly. So in the end it has the zero it has nullified the temperature gradient response when during its operation, whenever the force is applied. Here is another circuit of half bridge Wheatstone. Half Wheatstone bridges consist of two active strain gauges. We have the R1 and R2 are the strain gauge resistances. Simply, as we know from the previous expression of the full bridge, we get this relation, as we know that there is only change in resistance of R1, R2, and there is no R3 and R4 constant resistances. So we ignore the other factors involving the epsilon 3 and epsilon 4 are cancelled out. Only these two factors are involved as shown in this equation. And now move to the relationship, that delta R1 over R1 equals to minus R2 by R2. We have used this relation of the Wheatstone bridge relation. Balance condition, negative sign is due to the compression of the this strain gauges are arranged in such that when this is compressed, this is this stretch two opposite manners in the two opposite manners are placed, and negative simply we got this expression. After that, some formulation, we convert from this relation to this relation by simply putting the value of the gauge factor in it by delta R1 by R1, and we simply get this value, and sensitivity increased by a factor of 2 compared to quarter pitch factor we discussed later, and it has a more sensitivity as compared to the quarter pitch factor that discussed later. Almost the sensitivity is factor of 2 times is increased. In quarter bridge we have sensitivity reduced by 4 times. In quarter bridge, Wheatstone bridge, we have only one active strain gauge, and all of the resistance are constant. So there is only variation exists in the R1, and we know that all the strain gauges R4, R3, R4, R3 and R2 are the zeros change resistor. We know that the constant parameter P R3 by R4 equals to 1, because these factor cancel equals to 1. Simply put the value of 1 in this relation, we get this value, and other factors like the R4, R3 and R2 are cancelled. Only G1 epsilon 1 R remains, and simply put the value GF in the relation, we get this factor, and sensitivity in this factor reduced by 4. They have much lower sensitivity as compared to the half Wheatstone bridge circuit, had 2 times more sensitivity as compared to the quarter Wheatstone bridge. In some of the circumstances, we often encounter the error in the measurements of the strain gauge that may be due to the temperature effect. This can be compensated by the following techniques. Before moving on, let's discuss the graphs. On the right hand side, the above graph shows the variation in temperature, while there is also change in strain, which is not desirable one. We want the graph of this kind where when there is a change in the temperature, the strain graph remains constant at the zero line. This can be achieved by using the following techniques. Dummy gauge. In dummy gauge we use two strain gauges. One is active, other is dummy. These two strain gauges are made of same material. Whenever there is a change in the resistance or active, they also the same change in the dummy gauge resistance. As a result, the V-Stone bridge remains in a balance mode because these two resistances will nullify the effect of each other. As a result, we get a graph of this kind. The second or third active, 2 active and 4 active bridges are already discussed in the previous slides. In the last one we have self-compensation technique, where we have two other methods. Use of gauge. We use a gauge of same material having low temperature sensitivity, so they had minimum effect on the strain due to temperature change. And the last we had dual element gauge. We make use of the strain gauge having the two portions of the positive temperature coefficient and negative temperature coefficient. In positive temperature coefficient part, when there is a change in the temperature, the strain will increase. In negative, the strain will decrease. As a result, the overall effect will nullify the effect of the change in the resistance due to the temperature change. So hence we got the zero strain line as shown in the curve in this self-compensation technique. Let's discuss the problem of strain gauge. Here we had a Wheatstone bridge with one active strain gauge, and we want to determine the detector deflection of the galvanometer for 0.1% strain. We simply use the gauge factor formula and it determines the change in the resistance, and then we simply put the change in the resistance in this resistance value, and simply want to determine the change in the voltage between V1 and V2. We simply apply the Thevenin equivalent formula, and which also determines the resistance as a parallel configuration, and we end up with this circuit. And we want to determine this current. We simply apply Ohm's law and determine this amount of current flowing through the galvanometer. As for sensitivity given, 1 microampere is equivalent to 10 millimeter, and for 2.496 microampere is simply multiplied with 2.4 into 10. We get 25 millimeter deflection in a galvanometer. Now we discuss the piezoelectric force transducer. It was discovered by Pierre Curie and Paul Jacques in 1880. It works on a phenomenon of generating electric charge in material when subjected to the applied stress, and vice versa, mean it works inverse piezoelectric effect. When our force applied on the certain material like piezo material, it will reorient the positive and negative charge in a specific direction, thus that it established a positive on one side and negative on other side, and potential difference is established. Inverse piezo means when a voltage applied to it, it will generate some force on it, so it's a reversible effect and direction sensitive. It also self-generating, that is it is an active transducer. There is no need to supply the voltage to activate it. It is always an active. For compression result, when we compress a piezo material, it generate a positive voltage, while in the tension it generate the negative voltage. Piezoelectric behave in much the same way as a capacitor is working, is much the similar to that of the capacitor that stores the charges. Now let's take derivation of the piezoelectric force transducer. We have this kind of piezoelectric crystal. With the force apply, it generates output voltage, but this force should be dynamic. In terms of the static force, no output voltage should be generated, and there is a change in the respective thickness of the crystal. So we have magnitude and direction of the applied force is proportional to the polarity of charge produced. So we have of this form, we get Q equals to Kf, where K is defined as charge sensitivity, has a units of a coulomb per Newton. And as we require the output voltage, we simply apply the capacitance formula, because the piezoelectric crystal behave just like capacitance, where we have V equals to Q by C, where Q is it can be the K into F, and we simply put the formula of capacitance epsilon A by T, because there is a change in the thickness. So we simply call that K by E epsilon equals to G, which is called a voltage sensitivity, and we get this factor as there is a change in the elasticity. We can apply Young modulus, and after substituting the values of from 1 and 2, we get this type of formula: V naught equals to G, which is the voltage sensitivity, into Young modulus into a change in the thickness, which can be used in many type of calculation. This is a simple piezoelectric problem. You can do it yourself. Simply involve the formula as I drive in previous slide. Application of piezoelectric force transducer piezo motor. Or piezoelectric motor is a type of electric motor, but is different from the simple motor in that of comparison. It has piezoceramic that generates a force when a voltage applied to it. On right hand side, you can see there is a two trends. A piezoelectric device has a constant line that indicates that there is a constant efficiency of the torque as compared to the when to given amount at a given amount of power, where the linear electromagnetic device, which shows that it has low torque output as compared to the simple motor, and can use more precision encoders in the most of the application robotics and the other application like the camera lenses. These have the three categories: stick slip motor, stepper time motor, and resonant piezo motor. Stick slip piezo motor, it consists of the piezo and a slider. Whenever there is an input voltage, it causes the slider to move towards the left as indicated by the increase in voltage, and whenever there is a decrease in the voltage due to the inertial effect, the slider remains moved in one direction while piezo retracts. To perform in the precision fine task and 6 degrees of freedom robotic systems and also macro assemblies. Stepping piezometer consists of 3 actuators. C is involved for transition motion, where B is made contact with the slider. When C moves outwards, B make contact with it. In the other case, A makes contact. In this way, a walking phenomena is observed. It's used for long stroke, and with a free backlash makes them ideally used in scanning and as an encoder in many areas, and also used in picometers. It consists of 2 components, a slider and a piezo motor. Ultrasonic piezo motor generates electrical vibration. Due to this, it makes the slider to move lights towards left, and also used for good bidirection position repeatability, zero drift after position, and used for very high motion speed of 100 millimeter per second, very precise, and also it is noiseless as it is ultrasonic in nature, and vibrations are ultrasonics. Now we see the working phenomena of the piezoelectricity in the ultrasonic imaging. We have this kind of the suit which encloses the ultrasounds in the acoustic insulation, and we have the piezoelectric crystal enclosed in it as shown in this figure. And on the right hand side we have the working phenomena in which we ultrasound machine generates the voltages to certain piezo crystals that generate ultrasonic activity that will interact with the body and generates the corresponding ultrasonic wavelengths, and that will be intercepted by the ultrasound machine. It is explained by this figure that we have the certain wavelengths produced by the body, and there are some of the gas produced which indicate that these are reflected by a certain tissue, as indicated in this figure, that these tissue are indicated by white line borders, which indicates the cavity of the certain organ. As the brief explanation given below, the ultrasonic waves reflect in the interface between the media of the different density. The greater the difference in density, the more the reflection, so that's why tissue borders appear as bright on ultrasonic images. Comparison between a strain gauge and piezoelectric force transducer. Some of the specs like static measurements, accuracy, isolation, and moving cables. The strain gauge sensor is more reliable than a piezoelectric force transducer. while in other phenomena like the measuring range, rigidity and frequency range, time range, a piezoelectric sensor is more reliable than the strain gauge sensor. All depends upon the application on which we are using a strain gauge or a piezoelectric. Measuring force to the pressure. There are two types: hydraulic load cell and pneumatic load cell. Here is the schematics of hydraulic load cell. Consists of a piston and a fluid and a pressure gauge. When a force applied on the piston, it generates some pressure. As a result, is indicated by the dial. In pneumatic load cell, we have the air supply in it and have the diaphragm and having the flapper, which connected with the nozzle and dial gauge for indicator. Whenever force applied on it, there is a closing of the nozzle, and as a result, it generates some pressure in this pipe, and as a result, it is indicated by the dial. Here we have inductive force transducer called LVDT, linear variable differential transformer. The LVDT provides an AC output voltage signal which is proportional to the displacement of its core passing through the windings. On left hand side, we have a primary winding of moving core and a secondary coils A and B, which are connected in series configuration with each other. And output, we have the differential voltage. On right hand side, we have the graph illustrating the working principles of the LVDT. When we have the voltage signal applied at the input side, which is Vs, and correspondingly due to magnetic flux, voltage VA and VB will be induced at the secondary coils A and B due to mutual induction, which is given by this form. At a central position, when the core is at a central position in a graph, it can be seen at a null position. At this point, the differential voltage produced will be zero, because the voltage induced in a coil A and coil B are of same kind. In other case, when the core moves towards the coil A, or in the graph, it can be seen that it moves toward the positive side of the x-axis, then we have voltage produced on the output side of the Ka minus Kp into sine omega t minus phi, which indicates that the dominating factor of the voltage induced at a coil A as compared to the coil B. And when the core moves towards the coil B, as in the graph, it can be shown in a negative direction of the x-axis. We have the voltage induced more in the coil B as compared to the coil A, as given by this relation. Another thing you can notice that when the amplitude factor represents the amount of displacement of the core, whereas the phi represents the direction of the core. And one thing you also have noticed that when we move the core towards the A, there is increase of the amplitude, which it represents the amount of the displacement which is represented in terms of the force, and the phi also keep on increasing, which indicates the direction of the core in towards the coil A, whereas in coil B the amplitude it keeps on increases, whereas in phase we have the 180 degrees, because it indicates the direction of the core towards the coil B. Here is the working principle of the LVDT. In next slide, I will explain of its characteristic. Here we have the LVDT characteristics. As I already discussed in a previous slide, the information about the amount of the force is reflected in terms of its displacement is revealed by the amplitude of the AC signal, which represents the amount of displacement, whereas the direction of the core is represented by the phase of the AC signal. The advantages of the LVDT are they are quite linear devices, mean that it can measure in the range from the few micrometers to the few millimeters. Also do not have the friction part, which can generate the loss and creates a wear and tear of the core, so it can result in the increase of the life expectancy to about few years, and they can be enclosed in the non-metallic barrier for the use in the corrosive environments. Also, they are insensitive to the shocks and vibration. The main disadvantages are concerned with it that the presence of some harmonic or distorted signal at the input side that result in mutual induction and creates some amount of the voltage at the secondary side that results in the biasing in the output. Moreover, the secondary coils A and B, which I discussed earlier, cannot remain exactly the same, so that some amount of the voltage will always appear at the output side when there is no movement of the core. Here we have a simple problem of LVDT. It simply uses the open wording formula. You can also solve it by yourself. My part is completed now, and rest of the part will be completed by Mrs. Samula. Thank you.
Let us discuss tactile sensors. What are tactile sensors? Tactile sensor is a type of force sensor that measures information arising from physical interaction with its environment. They are used to measure how the forces are actually distributed in a specified area. In general, tactile sensors are used in fingertips of a robot. An array of tactile sensors is used in gripper of the robot to make it able to pick the objects with a force according to strength of its material. They are also used in touchscreen devices on mobile phones and other computing devices. There are multiple technologies used for the manufacturing of tactile sensors. For example, they can be piezoresistive, piezoelectric, and capacitive, etc. Piezoelectric tactile sensors. इनकी कंस्ट्रक्शन की बात कर लेते हैं. जो piezoelectric tactile sensor है ये 3 लेयर्स पे मुश्तमिल होता है. अपर और लोअर लेयर ये पीजोइलेक्ट्रिक मटेरियल से बनी होती है जिसका नाम PVDF है, पॉलीविनाइलिडीन फ्लोराइड. और इनके दरमियान एक सॉफ्ट फिल्म को सैंडविच किया जाता है. इस सॉफ्ट फिल्म का मकसद ये है कि जो वाइब्रेशंस यहाँ पे जनरेट हों वो इस सॉफ्ट फिल्म के थ्रू अपर लेयर में ट्रांसफर हो जाएं. तो इसका वर्किंग प्रिंसिपल ये है कि हम लोअर लेयर पे AC इनपुट अप्लाई करते हैं. चूंकि ये पीजोइलेक्ट्रिक मटेरियल है तो ये वाइब्रेट करेगा और ये वाइब्रेशंस इस सॉफ्ट फिल्म के थ्रू अपर पीजोइलेक्ट्रिक मटेरियल में ट्रांसफर हो जाएंगे और यहाँ पे वोल्टेज जनरेट करेंगे. तो जैसे ही हम यहाँ पे फोर्स अप्लाई करते हैं तो ये जो सॉफ्ट फिल्म है ये डिस्टर्ब होगी. इसके डिस्टर्ब होने से क्या होगा, जो वाइब्रेशंस यहाँ से यहाँ ट्रांसफर हो रही थी वो भी डिस्टर्ब होंगी और इसके अकॉर्डिंगली ये आउटपुट वोल्टेजेस भी डिस्टर्ब होंगे. इन आउटपुट वोल्टेजेस की फॉर्म में हम जो फोर्स अप्लाई की थी उसे कैलिब्रेट कर लेते हैं. सो दिस इज द बेसिक प्रिंसिपल ऑफ पीजोइलेक्ट्रिक टैक्टाइल सेंसर्स. यहाँ पे पीजोइलेक्ट्रिक टैक्टाइल सेंसर्स की वर्किंग लिखी हुई है जो कि पिछली स्लाइड में मैं डिटेल से एक्सप्लेन कर चुका हूँ. कैपेसिटिव टैक्टाइल सेंसर्स. Capacitive sensors are also used for measuring pressure, force, and displacement. A principle of operation of capacitive transducer is based on the equation of capacitance of a parallel plate capacitor. We know that C is given by A epsilon naught epsilon R over D, where C is equal to the value of capacitance. A is the overlapping area between the plates. D is the distance between the plates. Epsilon naught is permittivity of free space. And epsilon R is relative permittivity of dielectric medium between the plates. Capacitance of a parallel plate capacitor can be changed in two ways. The first one is changing distance d between the parallel plates, whereas second one is changing the area, overlapping area between the two plates. Change in distance. Capacitance is inversely proportional to the distance between plates. So as d decreases, capacitance increases and vice versa. Change in capacitance causes change in impedance, which can be measured by a bridge circuit. Sensitivity or change in capacitance with respect to distance can be given as S is equal to delta C over delta D, which is equal to minus A epsilon naught epsilon r over d square. This equation is obtained by taking the derivative of capacitor equation with respect to d. Change in overlapping area. As overlapping area increases, capacitance increases and vice versa. Here we can see two plates. The lower one is fixed plate and the upper one is movable plate. This plate can be moved towards left or right. As we move this plate towards left or right, this distance changes. So overlapping area can be given as this W width into this X. Since this W is fixed, so overlapping area is directly proportional to this X, which is equal to displacement. So capacitance can be given as C is equal to A epsilon naught epsilon R over D, which is equal to Wx epsilon naught epsilon R over D. Since all other things are constant, so capacitance is directly proportional to this displacement x. Its sensitivity can be given by taking the derivative of this equation with respect to this displacement x, which comes out to be W epsilon naught epsilon R over D. Cylindrical capacitor. Here two cylinders of different diameters are used. Cylinder with greater diameter is fixed, whereas cylinder with smaller diameter is movable. It can be moved towards left or right, which will cover a distance x. The value of capacitance between these two cylinders can be given by this expression. Here we can see that this capacitance is directly proportional to this displacement x because all other things are constant. So if we measure this capacitance with the help of a bridge circuit, then we can find the value of this displacement x. This arrangement can also be used to measure force applied on this face. To make this arrangement as force sensor, we can place a spring between these two faces. So when we apply force on this side, it will cover a distance x, which can be measured from this expression. So multiplying x with spring constant k, we can find the value of force applied on this side. Its sensitivity can be given by taking the derivative of this expression with respect to x. We have studied different types of capacitive transducers, where applied force causes change in capacitance. That change in capacitance need to be measured. For that purpose, we use this bridge circuit called sharing bridge. Unknown capacitance is placed here. The impedances of all the branches can be given by these expressions, where Z1 is the parallel combination of C1 and R1. Z2 is equal to R2, Z3 is equal to 1 by J omega C3, and Zx can be given as Rx minus J over omega Cx. Here Rx can be the internal resistance of this capacitance. In this bridge circuit, C3 and R2 are fixed, whereas R1 and C1 can be varied. When we apply force, change in capacitance occurs here. This causes imbalance of this bridge circuit. So we vary R1 and C1 such that this bridge becomes balanced. It will become balanced when this AC detector shows zero reading. So balance equation of this bridge circuit can be given as Z1 over Z3 is equal to Z2 over Zx. Putting the values of Z1, Z2, Z3 and Zx and rearranging, we get this expression. From here we can compare real and imaginary parts. Comparing this with this, we get value of Rx becomes equal to R2 C1 over C3. And the value of Cx becomes C3 into R1 over R2. We can also find the value of unknown capacitance in terms of output voltages. Voltages at node A and node B can be found by voltage division rule. So voltages at A can be given as Z3 over Z1 plus Z3 into input voltages. In the same way, voltages at node B can be given as Zx over Z2 plus Zx into input voltages. So output voltages can be given as voltage at A minus voltage at B. Putting the values of VA and VB, we get this expression. From here, we can find the value of Zx. So Zx will become equal to this expression. After putting the values of impedances, input voltages, and output voltages, we will get Zx, which will be equal to an imaginary number. From that imaginary number, a real part will represent the value of Rx, and from the imaginary part, we will find the value of Cx. Here is one capacitor sensor. An array of capacitor sensors can be made in this way. Here one electrode is common, while the other electrode is divided into multiple bars. Each bar represents a separate capacitor. So when a force is applied on a bar, change in capacitance is detected in that specific bar. So we will know where the force is being applied. Such arrays can also be made with the help of piezoelectric and piezoresistive materials that we have studied earlier. Such arrays are used on the fingertips of the robot and for the manufacturing of robotic skin. So robot will know what are the distribution of reaction forces from the object being picked by this robot. In the next two slides, I will be showing two videos that will demonstrate the importance of these tactile sensors.
Our core product is a revolutionary tactile sensor that measures all the same tactile parameters as the human finger. Here, we've got two of our tactile sensors mounted to this standard off-the-shelf robotic gripper. The manual handling task is very simple for a human to do. If you got any person and blindfolded them, told them to pick up this bottle, the moment they touched the object and attempted to lift, they'd be able to feel exactly how hard they need to squeeze to stop it from slipping. By enabling the feedback from our sensors, we can give this robotic gripper the same human sense of touch. In this case, with the feedback from our sensors enabled, all I need to do is tell the gripper to grip, and upon making contact, it can feel exactly how hard it needs to squeeze to prevent the bottle from slipping. And this is working in real time, so even if there are dynamic loads, for example, if I were to increase the weight, it would increase the force. If I decrease the weight, it will decrease the force, because it knows exactly how hard it needs to squeeze to stop the bottle from slipping. This is very useful in any situation where we might have an object that's crushable by excessive grip forces. So for example, if I want to pick up this box of biscuits, all I need to do to tell the gripper is tell the gripper to grip, and upon lifting, it knows exactly how hard it needs to squeeze. Or take this orange, which is not only crushable, but also has a variable size, weight, and shape. But again, all I need to do is tell the gripper to grip, and it can feel exactly how hard it needs to squeeze, even in the presence of dynamic loads. These are just a few examples of what our sensors can do. We've only scratched the surface of their potential application.
Now let us discuss torque measurement. What is torque? Torque is the turning effect produced by a force. It is the rotational equivalent of linear force. Measurement of applied torque is of fundamental importance in all rotating bodies to ensure that the design of rotating element is enough to prevent failure under shear stress. Torque measurement is also a necessary part of measuring the power transmitted by rotating shafts. So if we know torque on a rotating shaft, then knowing the angular velocity of the shaft, we can find the power being transmitted to the shaft. Different methods are used for the measurement of torque. Here we will study these four methods. The first one is measurement of reaction forces in shaft bearings. The second one is Prony brake. And then measuring strain produced on the rotating shaft with the help of strain gauges. And the last one is twist angle measurement. Measurement of reaction forces. In this method, magnitude of transmitter torque can be measured by cradling either power source or the power absorber. So here we place a force sensor. From the value of force sensor F and then multiplying this F with the arm length L, we can find the value of torque. Here note that for the measurement of torque with this method, we have to stop this shaft or we have to fully load this shaft. So by this method, we can measure start torques only. Torque measurement with Prony brake. It consists of a rope wound around a shaft. One end of the rope is connected to spring balance and the other end carries a load in the form of a standard mass M. Here weight is applied until this shaft stops rotating. So the effective force acting on this shaft can be given as this mg minus fs, and the effective radius can be given as radius of this cylinder rs plus radius of this rope rr. So we can find the torque as Fe into Re. In this method, a lot of heat is generated because of friction between rope and this shaft, and water cooling is usually necessary. Next method is measurement of torque by strain gauges. It is the most common method used for the measurement of torque. Previous two methods cannot be used for the measurement of torque in a rotating shaft. And in those methods, torque was not converted into an electrical signal. But with strain gauges, we can find the torque on a rotating shaft, and that torque will be converted into an electrical signal. In this method, four strain gauges are mounted on the shaft. These are connected at an angle of 45 degrees with this axis. Here note that these two strain gauges, strain gauge 1 and strain gauge 2, are on the upper side of the shaft. And these strain gauges are not on the upper side. These are hidden. These are on the back side of the shaft. In the side view, you can see the configuration of these four strain gauges. When we rotate this shaft anti-clockwise, then strain gauge 1 and 3 are under elongation, and the strain gauge 2 and 4 are under compression. So the resistance of strain gauge 1 and 3 will increase, and the resistance of strain gauge 2 and 4 will decrease. Shearing stress on the rotating circular shaft can be given by this expression. Here T is the applied torque, J is the polar moment of inertia of circular cross section, and D is the diameter of this shaft. Strain produced in a rotating shaft can be given by this formula. Here nu is the Poisson ratio and E is the Young's modulus. These two are the material properties of the shaft. However, we know that gauge factor of strain gauge can be given as delta R over R divided by delta L over L. Here delta L over L is equal to strain. So from here we can find the value of delta R over R as lambda into strain. So putting the value of strain here, we can find the value of delta R over R for 4 strain gauges in this way. Here note that negative sign with these two is due to reason that strain gauge 2 and 4 were under compression. 4 strain gauges must be connected in the Wheatstone bridge in the same order as shown here. This order is very important. If we place R3 here and R2 here, then it will create problem. Let's see how. We know that R1 and R3 were under elongation, and R2 and R4 were under compression. So when strain will be produced, R1 and R3 will be increasing, and R4 and R2 will be decreasing. So if we place R3 here and R2 here, what will happen? R1 will be increasing and R3 will be increasing with the same ratio. In the same way, R4 and R2 will be decreasing with the same ratio. So this ratio R1 over R3 will always be equal to the ratio R4 over R2. In this way, this bridge will always stay in the balanced condition, and we will observe no voltages at this output. Even the strain is being produced, but we are not getting any output voltages. So we always have to connect strain gauges in this order only. Unbalanced voltage of Wheatstone bridge can be expressed as delta R over R into applied voltages. From here we can find the value of torque, which becomes equal to this expression. Sensitivity of this transducer can be obtained from the previous equation. It is equal to output voltages divided by torque, which becomes equal to this expression. Here we see that sensitivity can be increased in two ways: by increasing applied voltages or by increasing the gauge factor lambda. But we can increase applied voltages up to a limit only, because these force strain gauges are resistances which have a maximum power rating. So we can increase applied voltages up to a limited extent only. The second thing is by increasing gauge factor. We can increase it by choosing the type of the strain which has higher gauge factor. Measurement of torque by strain gauges have two advantages. The first one is that it has a high sensitivity, and the second one is that torque can be measured in the rotating shafts. Its disadvantage is that it is difficult to connect this bridge circuit to the power source and to the output voltages, because these four strain gauges are mounted on the shaft and these are rotating with the shaft. So this whole part will be rotating with the shaft, and this whole part is stationary. So we have to use slip rings in order to connect rotating part to the stationary part. But these slip rings introduce some contact resistances, which causes some noise in the output voltages. So we have to be very careful while designing the slip rings for this purpose. Now let us discuss fourth method of torque measurement: twist angle measurement with the help of electrical torsion meter. When we apply torque on the shaft, it is twisted to some angle. This twisted angle can be measured by this arrangement. Here two discs are mounted on the shaft. These slaughter discs produce pulses in these transducers, and these pulses are leading to an electronic unit. When there is no applied torque on this shaft, these teeth of these two slaughter discs are perfectly aligned, and there will be no path difference between the output pulses of these two transducers. But when a torque is applied, the shaft will be twisted to some angle, and hence there will be a path difference between the output pulses of these two transducers. This path difference can be measured with the help of this electronic unit. So this path difference will be directly proportional to applied torque. Here I have written the working of electrical torsion meter that I have already explained. So here are three main advantages of electrical torsion meter. The first one is that there is no signal leakage problem. The second one is that there is no noise creation. Because we are not using slip rings here, so no contact resistance problem and hence no noise creation. The third one is that torque can be measured in the rotating shafts. Here are written some references for this presentation. So this is all from our side. You can ask if you have any question. Thank you.